Hello students, greetings of the day. Today I am going to start a very interesting chapter, that is system of particles and rotation. Generally students feel very difficult this to solve numericals if it is coming from rotation. So let us see how the concepts are made clear and then what are the key points while solving a numerical. So let us get started with the first subtopic, that is center of mass.
Center of mass. What is center of mass? Center of mass is simply a point, as it is written here, the point at which, if we assume whole the mass of the body to be concentrated, it has the same acceleration under the application of same force as for the whole body, then the point is said to be its center of mass. Let us consider this body here. If a force F has been applied on the body and it is having an acceleration A under the action of this force, then if we have to replace this whole body with a point mass and we apply the same force F, then it must be having the same acceleration. This point is called center of mass. If mass of this whole body is m, then we have to assume that at this point mass of the whole body is concentrated. Now why is it needed to define center of mass? See, till now whatever we had studied, it was only for particle. The motion we had studied, force we had studied, work, energy, whatever. We were considering all the bodies to be like a particle mass only, because never we bothered about their shapes, their size. But now onwards, we are going to consider shape and size as well. If it is a rigid body having some definite shape and size, of course it cannot be ignored. If we have to analyze its motion, the force applied on it, its dimension cannot be ignored. So what can we do? Because for us it is very convenient to use the laws of motion or to use the kinematical equations if it is for a single particle. We are confident in that. So now also we will try to substitute the whole body with a particle mass, and for this reason center of mass is needed. This is a concept which we have to apply to make all the bodies to behave like a particle-like mass. This is the concept of center of mass. Now let us see how it can be defined mathematically, because without defining mathematically, we are not in a position to solve a given numerical. So let us see how it can be defined. Mathematically, it can be defined for, now we have to consider two kinds of system. So first I am defining it for discrete mass system. Now what is this discrete mass system? It is a system in which mass is distributed all over the space. It is not concentrated, it is not continuous. So for discrete mass system, we have to define it like, let this be our discrete mass system. Here is a point mass m1, here is another mass m2, here is another mass m3. We have to write center of mass of this system. Of course, to locate a position, there must be some reference. So let us take that common reference to be O. Now with respect to this reference, if position of M1 is written as R1, for M2 if it is written as R2, for M3 if it is written as R3, then we can write RCM to be equal to, it will be M1 R1 plus M2 R2 plus M3 R3 upon whole the mass of system, that is M1 plus M2 plus M3. So this is how center of mass of the system is located. If we write it collectively, if we have to generalize it, because it won't be always for this specific system, then we have to write RCM to be equal to summation of Mi Ri upon summation of Mi. This is how center of mass for the whole system can be written vectorially. As you can see, R1, R2 and R3 all are not in same direction. So we have to apply vector addition here. This is position of center of mass for a discrete mass system where masses are scattered all over the place. Now what if the mass is continuous? Then of course we cannot write mass of each particle and their position. Like if we have to write center of mass of this board, it is not possible to write for its each consecutive particle. So then we have to write it as, second I am considering the continuous mass system. This time it has to be, as you all know, then for continuous system always summation sign is to be replaced by integration sign. Then it has to be equal to r dm upon integration of dm. Now for defining this is okay, we can define center of mass for a continuous system like this. But if we have to solve a numerical, we know that at this stage we cannot integrate a vector, because vector calculus is not yet included in our syllabus. So we have to write it in component form. For this, we can write RCM as XCM I plus YCM J plus ZCM K. So XCM can be written as integration of XDM upon integration of DM, and this integration has to be all over the body. Similarly, YCM can be written as integration of YDM upon integration of DM, and for ZCM also it can be written in the same manner, integration of ZDM upon integration of DM. This is how for a continuous and for a discrete mass system center of mass is defined. Now we are considering some continuous common shapes for which center of mass we have to derive. See, question of deriving center of mass is not going to come in your JEE or Neet exam, but you have to know how it is derived, because any step can be used for solving a given numerical. So you must be knowing how it is derived for a given shape, and then you can memorize few common shapes and their center of mass. So let us start with a semicircular wire. I am not including the regular shapes, that is the whole circular wire. Of course, center of mass will be at its geometrical center. The whole disc, again it will be at geometrical center. For sphere, for hollow sphere, for square, for cube, for all these shapes, center of mass will be at its geometrical center. But what if it is not that symmetric? Then we have to derive the value where it will be located. So first I am considering a semicircular wire. Now again, to locate center of mass, there must be a reference point. So let us take reference point at the center of this semicircle. This point I have taken as O, the axis chosen as X and Y. Let us now locate one small elemental mass here, which can be written as dm. So then it will be, if the angle here is theta, this should be a small increment in theta, that is d theta, and radius is r. So what is its x coordinate? It can be written as r cos theta and y coordinate as r sin theta. We have to separately derive both xcm and ycm. What about xcm? It can be written as we had written, it was x dm upon the whole mass. Let whole mass be m. Then this x can be written as r cos theta into dm. Now what is dm? dm should be mass per unit length multiplied with length of this small element, which is equal to r d theta, as you can see here. So this should be equal to mass per unit length. I can take outside, that is equal to mass upon the whole length is pi r. So m upon pi r, and inside it will be r d theta. So this becomes squared, and then d theta has to be divided by whole the mass. Now if we integrate, you can write limit has to be from 0 to pi. This value will come out to be 0, and it was not needed to derive it here, because you can check if it is symmetric about y-axis. If the shape is symmetric about y-axis, then obviously its center of mass will be having 0 x coordinate. It has to be along this line only. So now onwards, I am not going to derive the value of center of mass in the direction where it will be equal to 0 obvious from the diagram itself. Now we have to write YCM. It has to be equal to YDM upon the whole mass. Now what is Y for this particular element? It has to be equal to R sin theta. Again we have to write dm, that will be m upon pi r. M is here also, and then r d theta, so it will be r square d theta. Variation of theta has to be from 0 to pi. If I integrate this within the limits, it will be, these two got cancelled, 1 by pi r. This is minus cos theta within limits 0 to pi. If I substitute the values, it will be 2. So this is 2r upon pi. Now we got center of mass RCM for this shape as x coordinate 0 and y coordinate 2r by pi. You have to simply memorize the result, which can be directly used while solving a given numerical. One more case I am considering, center of mass for a disk, and it has to be a semicircular disk. So for a semicircular disk, because you know for the whole disk it will be at its center itself, so no need to derive for that. Let us consider this semicircular disk. Again I have taken reference here at center and these two as x and y axis. Is there any need to derive XCM? No. Again we can say that the given shape is symmetric about YCM, so directly we can write XCM to be equal to 0. Now we can consider, because already we know the value of center of mass for a ring, so this time I can consider the element to be that of a ring, which is having a radius small r. For this disk it is capital R and its thickness to be equal to dr. Now as we know the result YCM, directly I can write this to be equal to, for this element we have to write what is value of YCM for this element. It is equal to 2r by pi. Just now we had derived the result, so this can be written as 2 by pi r. For this element ring, radius is small r, so that one into dm. Now what is dm? Dm has to be equal to mass per unit area into area of this element. What is mass per unit area? M upon pi r square by 2 into area of this element, which will be equal to pi r into its thickness, that is dr. Now here variation for r should be equal to from 0 to capital R. If you solve it, you will get 4 upon these two got cancelled, pi r square, m is there, and here it will be r square dr from 0 to r. This will be 4m upon 3 pi r square. It will be r cube minus 0. 1 r square got cancelled, so it will be 4m. Of course this whole has to be divided by the total mass, that is m. Let us write it here. These two also got cancelled. This is 3 pi r. So we got value to be equal to 4r by 3 pi. This is how center of mass is located for a given shape. We got RCM having coordinates 0 and 4r by 3 pi. Now you have to memorize the result for some regular shapes. The shapes has to be, I am here writing the shapes, and you will just memorize all the center of mass, because this will be needed frequently while solving questions. Already we have derived for semicircular ring and semicircular disk. Now you have to memorize for, it will be a hollow semicircular shell, that can be written as hollow hemisphere. The next should be solid hemisphere, the next hollow cone, and then solid cone. So these are the shapes for which you must be knowing the value of center of mass. So do remember, all these has to be memorized. Now I am solving a question. Find the center of a uniform L-shaped lamina with dimensions as shown. The mass of lamina is 3 kg. This question is from NCERT book. Now it is an L-shaped lamina, but we can divide it into 3 squares, and as you can see, for these squares, because for a regular shape always center of mass will lie at its geometrical center. So if I write center of this square to be C1, here this to be C2, and for this one to be C3. Let us write coordinates for C1, C2 and C3. What it will be? For C1 it will be x coordinate, because this whole length is 2 meter, up to here it is 1. So it will be 0.5 and then 1.5. For C2 this will be 0.5 and 0.5. For C3 it will be 1.5, 0.5. So we replaced this continuous shape into a discrete mass system which can be represented like this. It is our particle mass C1, this is C2 and this is C3. And as mass of the whole lamina is 3 kg and these are all equal squares, so for each particle mass can be written as 1 kg. Now let us write as we write for a discrete mass system. xcm can be written as m1 x1 plus m2 x2 plus m3 x3. For all mass is 1 kg only. So it will be 0.5 plus 0.5 plus 1.5. And this whole divided by the total mass, that is 3 kg. On solving it will be 2 by 3 meter. Similarly for ycm we can write it will be equal to 1.5 plus 0.5 plus 0.5 and this whole divided by 3, which again is equal to 2 by 3 meter. Finally we got center of mass of this given shape, given lamina. RCM can be written as x coordinate being equal to 2 by 3 meter. So it is 2 by 3i plus 2 by 3j. This is how sometimes if shapes are having some symmetry, we can even convert a continuous mass system to a discrete mass system. Then there will be no need of integration. Simply we can write the summation. Now the next thing is about center of mass, that is motion of center of mass. Now we have its position RCM. So how its motion is defined? Okay, let us first get velocity of center of mass, and as we know it can be written as dRCM upon dt. This is velocity of center of mass for a body having some definite dimension. Similarly we can write ACM as dVCM by dt. Now as we know, VCM can also be written as, either if we have the value of RCM we can differentiate it, or directly it can be written as summation of MIVI upon summation MI. This will be for a discrete mass system. Now I am generalizing the definition. Whatever it was for position can be applied for velocity as well. So for discrete mass system we can define velocity of center of mass as like this. Continuous mass system, it can be written as dmv upon integration of dm, that will be mass of the whole system. In the similar manner we can write for acceleration as well. So it can be written as summation of MIAI upon summation of MI. And for continuous mass system it will be, it has to be one vector sign also has to be there, dma upon integration of dm, that is equal to mass of the whole system. Here I have applied vector sign, you can see even for continuous mass system, but do remember while solving you have to write separately for v along x, y and z if it is a 2D or 3D motion, and similarly for a also. So in this manner we can define motion of center of mass. Now let us see one thing. ACM can be written as summation of MIAI, right? And upon this upon M. So from here we can write M, if take on another side it can be written as MACM upon, now this is summation of MIAI. What does it mean? MA can be written as F, so it can be written as summation of Fi. This is very important concept, which can be further written as F1 plus F2 plus F3 and so on, will include the number of particles as there are in the given system. So now we can write that sum of the total forces acting on the system has to be equal to mass of the whole body multiplied with acceleration of center of mass. This is from the definition of center of mass itself verified here, because center of mass must be having the same acceleration as the whole body if the same force is applied on it. We had said this earlier, and here you can see that this is now verified with the given expression. So now we can write MACM to be equal to summation of all the forces. One more very interesting thing can appear from here, that if forces are only mutual interaction, if we are considering a closed system in which there is no external force is there, in absence of external force, then we can write this summation has to be equal to 0, because the forces will be action-reaction pairs, and then ACM has to be equal to 0. So we can write that if we can say that if no external force is acting on the system, acceleration of center of mass has to be equal to 0. Just now we have seen in motion of center of mass that if no external force is acting on the system, then center of mass, if initially it was not moving, it will not move at all. And based on this concept, here is an example. The balloon, the light rope and the monkey shown in figure are at rest in the air. See, here the whole system is in rest, so of course center of mass also must be at rest. Now if the monkey reaches the top of the rope, by what distance does the balloon descend? Mass of balloon, mass of monkey and length of rope ascended by monkey is provided here. So let's see how to proceed in this question. Now as no external force is acting, because monkey will apply a force on rope and in reaction rope will apply a force on monkey. So these two are forces of interaction kind which cannot displace the center of mass. Then we can write delta XCM to be equal to 0 for this whole system. Now what is delta XCM? Delta XCM can be written as mass of monkey multiplied with delta X for the monkey plus mass of balloon multiplied with delta X for mass of balloon upon the whole mass, that is M plus M, and this has to be equal to 0. Now what is delta XM? That is displacement of monkey. It should be written as displacement of monkey with respect to rope plus displacement of rope. And what is displacement of monkey with respect to rope? It has to be L in upward direction. So that is L. Now if we consider that the rope or the balloon has come down by Y, so it will be equal to L minus Y, because this Y is in opposite direction. And from here we can write M multiplied with L minus Y minus M, because displacement of balloon is Y taken in downward direction. This should be equal to 0. On solving, it will be ML minus M plus My to be equal to 0, and then Y is equal to ML upon M plus M. So this is the distance by which the rope or the balloon has to descend, while the monkey has ascended up by a distance L on the rope. You can see how I have applied the concept that delta XCM should be 0 if there is no external force acting on the system. If whatever be the event, it is only due to mutual interaction between the constituent particles, always we can apply this formula. I am leaving this topic here itself, but in next session I will elaborate this concept, which will be very useful to solve a lot number of numericals. So we will see in detail what does this mean physically and mathematically when we write that MACM is equal to 0, though different forces are there inside the system and particles are having accelerations inside the system. Still, for the whole system we can write acceleration to be equal to 0. Till then, keep waiting for the next session. Bye.